Okay, so in this video, we're going to sort of think our way through how it is we are going to calculate this deflection numerically. So it all starts off with this equation. This is the equation that fuels the entire process, and this is our differential equation of the deflection curve. Now, we've seen this guy many, many times. Now, as I said in the previous video, our usual approach to this is to work out some function, right, some function of x, right, that describes the bending moment, and then integrate both sides of this equation twice. That will leave us with some constants of integration, some unknown constants, and we use boundary conditions typically to solve for those unknowns. Now, our approach this time is going to be different. We're going to, as I've said already, we're going to take a numerical approach. So we need a way of calculating the deflection, i.e. doing the integration, that doesn't require much manual input from us. We only want to feed into this process the values of the bending moment at each position along our beam, and that's basically it. We want to then write the logic that allows the whole process to flow from there. So we can't sort of be stepping into the process, you know, working out what are the equations for m as a function of x and so on and so forth. And so our numerical solution is going to really help us. Our numerical integration is really going to help us in this. So in order to sort of move this along, we know conceptually what it is we're trying to do, and we have a sense of how this numerical solution is somehow different from this analytical solution. But let's actually dig down into the nitty-gritty of it now and actually work out what it is we're going to do. So let's think about this from very first principles, from the basics. What is an integration, right? An integration fundamentally is just a way of establishing the area beneath a curve, right? That's one way of conceptualizing it. So let's just make a note here that just says fundamentally we need to use numerical integration. So let's ask the question. What is an integration? It is just the area beneath a line between two limits. That's it. All right, so let's just sort of expand this idea a little bit. Let's just imagine an xy plane. So we have x in the horizontal axis and some function of x in the vertical axis, and let's imagine we have some curve. Now that curve, just an arbitrary curve, or in the context of our discussion, it could be the bending moment diagram, right? But for now, let's just call this some function of x, right? That's all that is. And we can imagine at some point along that x-axis, we'll define a point A, and at some other point along the x-axis, we'll define a point B. Now, if this is very basic for you and you're very comfortable with integration, bear with me, because we're going to advance from this pretty quickly. I just want to make sure that everyone's on the same page here. So, integration, what is integration? It's a way of working out what that area is, right? And so if I was to write out an equation that sort of captured what is integration, or basically captured mathematically what I've just said, we would say the shaded area is going to equal the integration, right, between a and b, between the limits of f of x dx, right? That's all we're trying to do here. We usually take this function of x and we apply our analytical integration rules, and there is textbook after textbook explaining all of these various different rules, right? But like many things in sort of engineering analysis, the analytical approach only gets us so far because it works for a certain subset of conditions usually. I'm speaking generally now about analytical approaches or solutions versus numerical solutions. Analytical solutions are usually the accurate solution, let's say, for want of a better term, but they're quite limited, okay? And so that's where numerical solutions come in. And this deflection approach, or this deflection calculation that we're going to do, is no different. It's very versatile, and that's why we're using it as the basis of our calculator. So how would I do this integration numerically? Well, it comes back to something that we've all learned about at some point in our schooling past, and that was the trapezoidal rule, or Simpson's rule is another one. And these are just algorithms that we can implement to calculate the area under a curve. Now, the trapezoidal rule is the one that we're going to use. I'm not going to dig into any derivation of it or anything like that. I'm just going to state it. If you're watching this video and you've gotten this far, there's a very good chance that you've seen the trapezoidal rule previously, so I won't labor it here. I'll just say to do this numerically, we use the trapezoidal rule. All right, so let me just sort of sketch out here a diagram to go along with this explanation. So again, we're going to have a similar xy plane. We're going to have a function of x, again, could be, not getting ahead of ourselves, but that function could be the bending moment. Now what's different here is, what's different with a numerical solution is we don't have an equation that describes that curve, but what we do have is the values of the function, right? We have the values along that curve, or the values along the curve at a fixed interval. So what have we got? Let's call this position x0, let's call this one x1, x2, and so on and so forth, all the way down to xn, right? Which would make, keeping this in sort of general terms, right, this would make that the function of x evaluated at x0, the function evaluated at x1, etc., all the way down to f of xn. Now we don't have a function. This is just a longer way of saying this could be m0, this could be m1, and this could be m subscript n. Okay, the area under that curve is basically, let's say the area, according to the trapezoidal rule, we won't use equals, we'll be specific here, and we'll say that it is not equal to, but it is approximately equal to the interval, right, the x interval, let's call that delta x over 2, the x interval over 2, times the value, the first value, let's call it fx0, plus 2 times fx1, plus the same again, 2 times fxn minus 1, right? I'm going to sort of break this up now in a second, plus fxn, right? Okay, so that is the trapezoidal rule. What is that saying? That's basically saying this guy, I take 1 times the first value, 1 times the first value, remember they're just bending moment values, I take 1 times the last value, and then I take 2 times all of the values between the first and the last. That's what that's signifying there, right? So this is the basic mechanism. This is our basic mechanism of integration, right? The basic algorithm of integration that we're going to use to define or to determine our deflection. But this still has some challenges, right? This is just the basic mechanics of how we would perform the numerical integration. There are still some challenges that we're going to need to address within this. So to sort of pick apart these challenges and to really highlight them, let's think about the actual process. So up until now we've just talked about the mechanics of doing a numerical integration, but let's actually see how that maps onto our challenge or our task of calculating the deflection. So let's think through the deflection calculation process. Let's use this tool and put it into practice. Okay, so I'm going to set up 3 XY systems here, right? So 3 sets of coordinate systems. So on this we'll call it XY system for now, right? So on this system here, we're going to have on the x-axis the x values along our beam. On the y-axis, we're going to have, at each x value, we're going to have the value of the bending moment. Remember, we're assuming we have that. So let's just call it m of x, and we're just going to divide it by EI, right? And what that allows us to say is that this thing here, this vertical axis, has got values of d2v dx2, right? So remember, we have all of the m values, and we're assuming we know what E and I is. So we have all of the numbers that make up this top graph. Let's define a whole series of vertical lines here. You'll see why now in a second. So we're saying we've got some value here. I'm just going to, instead of using the m over EI, let me just for shorthand just say m for now. So that's just going to be m0, and we're going to have another value here. Let's call that guy m1, noting that it's actually m over EI, but I don't want to write m over EI every time. This is going to be m2, and this is going to be m3, and so joining the dots essentially with a straight line between each point is what gives us our bending moment diagram. So that's the information we're starting with. Now let me define another XY system below this guy. So that's going to be this guy down here. Again, the x-axis is common. This is every position along the beam, but the y-axis is going to be, the vertical axis is going to be the rotation, right? So that's going to be theta x, and that's going to be the output of an integration. If you do an integration of d2v dx2, you integrate that once, you get dv dx. Okay, and that dv dx, That's going to be the output of our first pass of integration. And we're going to trace down these dashed lines because I want to relate the values of moment at each position along the beam with the values of rotation that we're going to calculate. We'll leave that for now, and then we're going to come down and define a final set of axes, and this set of axes is going to be where we represent the deflection. So x again and v of x, now v being the deflection. So again, you can think about, I would get all of the values on this second graph here by integrating all of the values in the top graph here, and then I would get all of the values in the bottom graph here, the v graph here, by integrating all of the values in the middle graph here, right? So we're going to sort of work our way down through this integration process and see how all of these values come about. All right, now we're ready to start sort of applying the brain here. So what have we got? We've got all the bending moment values. Now, if I think about what I want to try and achieve, I want to work out for every point along my beam, I want to work out what would be the corresponding rotation, right? Because I can't get down to deflections until I've dealt with rotations. So let's see. I'm going to start off and I'm going to show it in green here for a very specific reason, which I'll come back to. I'm going to start off here and I'm going to assume I know the value here, and I'm going to call that value theta 0, right, corresponding to m0 above there. Now, assuming I know that value, well then I can come along and I can calculate numerically, using a numerical integration, what is this value here, right? So this one's going to be theta 1. So how do I get theta 1? Well, using the trapezoidal rule, right, I'm going to say here that theta 1 is going to be whatever theta 0 was, okay, so whatever the previous rotation was, or the rotation at the previous step or position in the beam, plus, now this is where my numerical integration comes in. Remember, I'm integrating m over ei to get rotation. How do I do that? I use the trapezoidal rule. What does the trapezoidal rule look like? It is half of the interval, let's call it delta x over 2, times, remember, 1 times the first value plus 1 times the last value. Now I only have a first and last value, right? The first value is going to be this guy here, and the last value is going to be that guy there. There are no values in between, right? So I'm going to have half the interval plus, let's call it m0 over ei plus m1 over ei, right? So that is going to be how I get theta 1. Assuming I know theta 0, right? Assuming I know that guy, assuming I know the moment m0 and I know the moment m1, that means I can get theta 1, right? So I'm going to say that this guy here is the trapezoidal rule, right? It's approximately the area under the line between m0 and m1, right? And think about all that is the average value of m over ei. So it's like taking this value here, right, the average value, so it's m, think about it, m0 plus m1 divided by 2, that gets you your average value, that gets me that guy there, and then I'm multiplying that height, if you like, by this width, delta x, and that is essentially giving me that shaded area there, right? Again, remember, the integration is just the area under a line. So that's how we've gone and worked out theta 1. Now what we want to do is generalize that. In fact, let me finish writing my note here. We'll say that that is the trapezoidal rule, right? And I'll just say it's an approximation. It's an approximation of the area under the line. All right. So we want to generalize this, right? So we just want to have a statement that can apply for any values, right? So we can say, let's generalize. So what do I mean by that? Well, theta, some value theta I, is equal to theta, the previous value, which would be I minus 1, right? Plus delta x over 2 times mi minus 1 over ei plus mi over ei. That's what I mean by generalize, right? So you can put in any value of I and this equation would work. Now that we've generalized it, we can go ahead and use the corresponding values of moment to work out what are all of the other values of theta. So theta 2 and let's just say theta 3 here. And so in that way we can step through all of our bending moment values and we can work out, let me just put that, I'm coming back to the reason why that's in green now in a second. Then we can use our numerical integration to get all those values. So then it's just a rinse and repeat. We take these values here, these rotation values, and we apply the same logic and we work out what are the V values, right? So now let's think about how we do this. We're assuming, again, that we have an initial displacement. Let's call that V0, again in green, because we have something more to say about that. And we can do the same thing. We can do a numerical integration where we say the value at V1 is whatever the value was at V0, and we just apply our trapezoidal rule, right? So that looks like delta x over 2. This time it's theta 0 plus theta 1. And again, when you generalize that equation, you get Vi, so some value Vi is whatever the value before it was, Vi minus 1, plus delta x over 2. We're assuming a constant value of delta x, by the way, a constant interval. And this is going to be theta I plus theta I minus 1. That's your general equation. So in fact, let me put some boxes around these because they're important. The process evolves like this. So we'd end up with another value for V down here. We'd call that one V1. We'd end up with another one we'd call V2, and another one we'd call V3. And then you could join the dots, and that is your deflected shape, right? That's the end result. That's what we're trying to get to. Okay, so now there is a weakness in this approach. There is an issue that we're going to have to write some logic to address. And you probably spotted it already, but it's this. The whole thing hinges on whatever value this was, right? If that was the wrong value, well then everything that flows from that, right, all of the subsequent theta values and therefore all of the deflection values, well, they're going to be wrong, aren't they? It all stems from this, and so that's kind of, you could think about that as a potential weakness in this system. This whole thing starts off with a guess, right? A guessed value of theta 0, right? So I'll say need to guess, right? Exclamation mark, because we don't like guessing, right? So a value here, we need a value here. So we need to guess a value here, and then at the end of the process, we need to test somehow if that was the right value. And if it wasn't, we need to repeat the process, and we need to keep repeating the process until we get what we're going to call, in air quotes, the correct value for theta 0. And so that guess, or that check, if you like, is going to be the subject of what we talk about next. So let me just say, we need to guess a value here and test if it was the right value at the end. And so I said there was something else I wanted to say about this value of V0. Well, if you start your integration process, if you start at a support, well then you know V0 is going to be 0. The vertical deflection at a support is going to be 0. So I'll just say that's a bit of an easier one to deal with, right? So if we start at a support, which is the obvious thing to do, we know this is 0. Right, so that leaves us with one final thing to discuss. How do we work out the correct value of theta 0? Okay, ultimately, how do we call our calculation complete? In other words, how do we know that we've chosen the correct value of theta 0? Well, it's actually a pretty logically, it's a very straightforward thing to think about or conceptualize. Let's start off with a quick heading here. Let's just say testing our guess for theta 0. We need some kind of test, right? So we need some way of testing what our code gives us against something we know to be true, right? So that means we got to ask ourselves, well, what do we know about the deflection for this beam? Well, the thing that we know is that the deflection at the other support must be 0. Well, we're assuming our beam has at least 2 supports here, right? And if we started at, let's say, the left support, and then we go ahead and we calculate the deflection all through our beam, well, we know that the deflection at the other support, it must be 0. If we've calculated or if we've guessed the correct value for initial rotation, well then the deflection that we get for the other support must be 0. And that essentially forms our test. That's the basis of our test. So say we guessed or we assumed, right, theta 0 is just any random number off the top of your head, right? 0, let's just say 0.002. That's not a significant number, that's just any number, right? So let's say we guess that value and then we go through the whole process and we get the following. We get a deflected shape, but we end up with something like this. Let's imagine our beam was some simply supported beam. A beam that looks like this. Support on the left is a pin, support on the right is a roller. And we guessed our initial value. Again, throw some loading on it there. And we ended up having some deflection that looked like this, right? Well, it's very easy for us to check and see, well, what's the deflection on the right-hand support? And if it's not 0, if it's anything other than 0, that value is going to be our error. And so by observing what this error is, right, is it an error where the deflection is below the support, or is it above the support? That's information that we can use to alter our initial guess and try again and repeat the process again, right? So let's see, what would that look like, right? So if I was to say, let's say VB, let's say that was A, and let's say that was B, and so VB was the vertical deflection at support B, and I suppose we could then say that VB is our error, right? If VB, if that happens to be below, let's just say it was below, well, that would mean our initial value of our rotation, our initial value here for theta was too big, right? And so we need to reduce it, right? So we'd say therefore, let's go back to black. We'd say therefore we want to reduce theta 0 and try again. On the other hand, if VB is above the support, well, then we'll increase theta 0 and try again. Okay, so what we're saying here is that this is actually an iterative process, right? This is an iterative process to identify theta 0, a value of theta 0 that minimizes the error. Right, so there you have it. That's the process. It's an iterative process, and because the computer is going to do all of the hard work for us, it's going to crunch all the numbers. All we really have to do is implement the logic. So we'll do something like calculate or write a function that's going to calculate the deflection. We'll then write some code or some logic that checks that error and then recalls our function, alters our initial value of theta 0 and recalls the function, and then checks the error again. And we're going to keep doing that until we get our error within acceptable limits. So that's the basic workflow that we're going to implement over the rest of this project. Okay, so this video is definitely the most important video to understand for this whole project. The rest of it from here on is just coding and implementing this logic that we've talked about in this video. This one is the key one. So if you haven't understood it, make sure you spend some time, go back and make sure you understand this one, because as I say, this is the important one. After this, all we're doing is writing some for loops, some while loops, some functions. Pretty straightforward from here on. Alright, so in the next video, we're going to dive into our Jupyter notebook and actually start writing the code. So I'll see you in the next one.